Hi everyone, it's Nicolas Trevisan from P2design, also known as CoolCat VFX. Long time no see, huh? A while back, we asked you, the community, to choose which game engine you would prefer for future VFX content on the channel, and Unreal Engine was the most popular choice by far. So, in today's video, we're going to use Unreal Engine 5.1 and the Niagara VFX system tool to create some cool sparks and lightnings, an ideal passive effect to attach at the end of a swinging cable in sci-fi environments like this one. We'll create basic materials and paint our own lightning textures, play around with Niagara's emitters modules, and see how to parent an effect to the bone of a skeletal mesh. So let's get to work, people! First, let's have an overview of the hierarchy of our effect. It is made of 3 different layers: a subtle blurred halo, some sparkly sparks, and some shiny lightnings. We'll start by creating the subtle blurred halo layer. For that, we'll need a basic alpha blend transparent material, a blurred halo texture, and 2 Niagara emitters. Let's create our first material. We want a simple material that handles transparency and allows us to control our particles' color and transparency. Right-click in your content browser and add a material. We will edit it by double-clicking on the material asset in your content browser. In the detail window, set the blend mode to translucent and the shading model to unlit. We don't want our particles to be affected by the lighting of our scene, and it will make our material less heavy performance-wise. We need to reference our texture first. So we'll right-click in the graph panel and search for the texture parameter 2D node. Being a parameter, this node will allow us to reference, if we want, a different texture on each material instances that we'll create later on in this video. We want to control our particles' color and transparency. The node that we need for that is simply called particle color. To control the color of our particle, we'll connect the RGB channel output of the particle color node to the emissive input of the master node. To control the transparency of our particle and our texture, we will multiply the particle color node's alpha output to the RGB output of the texture node, and link the result to the opacity input of the master node. And we already got our material done. We'll save it and close the material editor window. We can now right-click on our material asset in our content browser window to create a material instance where we'll be able to reference our blurred halo texture that we are going to make right now. To make this type of texture, you can use softwares like Adobe Photoshop, Krita, or GIMP. In my case, I'm using Adobe Photoshop. After creating a 512 by 512 document, I'll use a simple soft brush. Apply one big stroke at the center of the canvas, and apply a second one but with a smaller radius at the center of the first big stroke. My texture is done. I can now export it in JPEG on my desktop and import it to Unreal Engine by right-clicking on the content browser, selecting the Import to option, and selecting my JPEG file. After we've imported our texture, we'll be able to assign it to our material instance we've created a minute ago. Open your material instance, tick the texture option in the global texture parameter values submenu, and search for your blurred halo texture. Alright, we made our transparent material, our blurred halo texture and material instance. We can now start to create our effect. Right-click in your content browser and create a Niagara system. We will create an empty system. After opening our newly created Niagara system, we'll set up our preview window and get rid of this bright environment to replace it with a neutral color. We'll customize our preview window by going to the Window tab and click on Preview Scene Settings. In this window, we'll go to the Environment subtab, untick Show Environment, and pick a dark gray color in the Environment Color parameter. That's much better. We'll be able to easily perceive our effects with this preview background color. You can then save these changes by adding a profile right there. We'll also deactivate the default auto exposure post-process filter in the preview window by going to the Lid tab, untick Auto, and set the EV100 parameter to 0. That way, we won't have any exposure variations on our rendering camera. Now we can finally start to create our Niagara emitters. We want 2 emitters. Both will be spawning a single looping particle, but one will be emitting a big dark particle, and the other a brighter but smaller one. This will bring contrast and a bit of focus to our effect. We'll start with a dark particle emitter. In the system overview, we'll right-click and select Add an emitter. By chance, we already got the perfect template for that, the single looping particle template, so we'll choose this one. The only things we will have to change are mostly located in the emitter properties and initials particle module. In the emitter properties, our particles are currently emitted in world space. And we don't want our particles' position to be relative to the world, but to our emitter itself. So we'll tick the local space parameter to constrain our particles to act as children of our emitter and follow the current location of the emitter. In the initials particle parameter, we'll change the color and size of our particles. In the color mode submenu, select Direct Set and choose a dark tinted color with a low alpha value. We want something subtle here that supports and brings contrast to our future sparks and lightnings particles. In my case, I want blue sparks and lightnings, so I'll go for dark blue. In the sprite size mode parameter, I'll select the uniform scaling mode and set the uniform sprite size value to 250. It is important here to note that all values that I'll be using during this video are related to the size of my scene. So feel free to adjust those to fit your needs. And finally, we'll change the current material by our handcrafted Blood Halo material instance by going to the Sprite Renderer module and assign our old material right there. We got our first emitter done. To make the brighter and smaller Blood Halo emitter, just duplicate our Dark Halo emitter by selecting it and pressing Ctrl+C and Ctrl+V. In the initialized particle module of the duplicated emitter, we'll trick the color and alpha value of our particle. By going above 1 in the blue channel here, I'm making my color starting to emit light. I'll also reduce the uniform sprite size value to have a smaller particle. And we are done with this part. After selecting an emitter, click on its name to be able to rename it. You can also select both emitters and right-click next to them to add a comment to group them and keep your system overview window clean and organized. We can already drag and drop our Niagara system directly into our level to have a better visualization of its behavior within our 3D environment. We'll continue this tutorial video by making those bright lightnings. For that, we need a basic transparency dissolved material, a lightning sprite sheet texture, and one Niagara emitter. You might ask yourself, why would we need a new material and not just use the one we just created? Well, mainly because a dissolved effect at the end of our lightning particle's lifetime will be pretty good looking and less boring than a regular opacity fade out. We need this new material to handle transparency, to allows us to control our particles' color and transparency, and let us have the possibility to control a dissolve effect directly through our Niagara emitter. We'll save some production time by duplicating and renaming the basic transparent material we've created for the blood halo earlier in the video. The only things we need to add to our newly duplicated material is a smooth step node and a dynamic parameter node. The smooth step node will make a smooth transition between the minimum and maximum threshold. The dynamic parameter node will allow us to use a parameter directly from our Niagara dynamic parameter module. This will be handy to control how the dissolve effect evolves during the lifetime of our particles by using said parameter as a curve. We will plug the RGB output of the texture node to the value input of the smooth step node, and the red output of the dynamic parameter, which we can rename in the detail window, to the mean input of the smooth step node. The output of the smooth step node can be then linked to the B input of the old multiply node that was here when we created the blood halo material. And that's pretty much it. Thanks to the Niagara dynamic parameter module, we'll be able to adjust the smooth step minimum threshold value to control the dissolve effect of our lightning particles during their lifetime. We'll also be able to make them entirely fade away with the particles alpha at the very end of the lifetime if necessary. We got our material ready, and now we need our lightning shapes. We can already create a material instance where we'll be able to reference the lightning spreadsheet texture that we're going to make right now. In Photoshop, I'll create a 512 by 512 document. We will make a spreadsheet containing 4 different lightning shapes, randomly picked and applied on each particle. If you want, you can make more. In Photoshop, we got a tool that will help us visualize the texture area occupied by each sprite, the grid tool. It can be activated by going to the View menu, Show, and selecting the grid option. To configure the grid tool, go to the Edit menu, Preferences, and click on the White Grid and Slices option. Here, you'll be able to configure and customize the grid tool. I'll personally make a 2x2 spreadsheet, so I'll need my document to be divided in 4 equally sized areas. Now that the grid tool is set up, we can draw our lightning shapes. You can paint stylized lightnings by making some spiky and angular shapes with a round hard brush, while having some width and length variations to keep their visual varied and not too regular. You can even add some additional branches. Keep in mind the scale of those lightnings. They will be used for a small effect at the end of a cable. So keep your lightning shapes short and small, without too many segments or branches. We aren't making lightnings for a thunderstorm here. To make the texture rock with the dissolve material we've made, we'll need some darker and lighter values to guide the dissolve effect inside the shapes, and make the darker part fade away before the lighter ones. To darken parts of your shapes, you can use the eraser tool with a low opacity on a soft brush, and apply some strokes with various sizes on some parts of your lightning shapes. Finally, we'll make these lightnings glow. Duplicate your layer, go to the Filter menu, Blur, and select the Gaussian Blur filter. Then, above the layer we just blurred, select the Screen Blending mode and lower a bit the layer's opacity. And we are good to go! After you've imported your texture in Unreal Engine, don't forget to assign it in the material instance you've made before painting your lightning shapes. Alright, we made our transparent material with the dissolve effect, our lightning spreadsheet texture, and metal instance. We'll now proceed to bring those lightning shapes into life in our Niagara system, already containing our blood halo particle emitter. We want this emitter to continuously spawn particles with one out of the 4 lightning shapes we've painted applied to them. We want these lightning particles to have variations in lifetime and size. We also want them to dissolve and fade at the end of the lifetime. We'll add an emitter in the system overview next to our blood halo emitters and choose an empty template, for no other available templates will suit our needs. In the emitter properties, we'll tick the local space parameter to constrain our particles to spawn in local space. In the emitter update stage, we'll use the plus icon to add a spawn rate module to continuously spawn particles. We don't want a float value here, this would get us a stable and boring emission rate. Instead, we want some randomness where sometimes no particles are emitted. To do that, we'll click on the little arrow next to the spawn rate parameter, and we'll set the parameter type to random range float. We'll set the minimum value to 0, and the maximum one to a higher value. In my case, 10 seems to be good. Not too little, not too much. Now, we want our particles to not look like little glowy dots. We want some lightnings. In the sprite renderer module, we'll assign our lightning metal instance in the metal parameter and type the number of columns and lines of our texture spreadsheet in the sub-image size. In my case, it's a 2x2 spreadsheet with 2 columns and 2 lines. This would be important for our next module to be able to correctly read, select, and apply a sprite from our spreadsheet to a particle. This next module will add it by pressing the plus icon next to the particle update stage and searching for sub-UV animation. First, let's fix this warning by selecting Sprite Renderer in the Sprite Renderer parameter. We'll then set the sub-UV animation mode to random and set the evaluation type to spawn only. Now, our particle emitter is able to read our spreadsheet texture from our metal instance, pick and apply one random lightning shape out of the 4 available ones of the spreadsheet. We can't see our randomly picked lightning sprites yet because we are not using the dynamic parameter module. We'll make them dissolve by adding to the particle update state the dynamic metal parameter module. This module, as the name suggests, is linked to our dynamic parameter node in our dissolve material we created a minute ago. We'll activate the first dynamic parameter, corresponding to the red output of our dynamic parameter node in our material, and since we want the dissolve effect to evolve during the lifetime of our particle, we won't need a simple float for our parameters type, but rather a float from curve. In the curve editor, I'll select an S template and push the left handle of the second key down to get an ease-in curve going from 0 to 1. Now that our dissolve effect is working, we can add, if necessary, an opacity fade-off effect to make sure all lightnings completely disappear at the end of the lifetime if the dissolve effect doesn't eat away all parts of the texture. To do that, in the particle update stage, add a scale color module. In the scale alpha parameter, set the parameter type to float from curve, and choose a reverse S template. That should do the job just fine. We'll now edit the timing of our lightning shapes and add more variations to them. In the initialize particle module, we'll change the lifetime, color, size, and rotation of our particle. We'll start by fixing our lightning's timing and pop, because right now they have so much lifetime they don't feel impactful at all. In the lifetime module, I'll set the lifetime mode to random to get variations on the lifetime, and set small values something between 0.1 and 0.2 seconds will be good. In the Color Mode sub-menu, select Direct Set and choose your desired color. Personally, I'll go for an intense blue with a high value to make it shine. In the Sprite Size mode, I'll select the Random Uniform Scaling mode and set a high value range in the Uniform Sprite Size. In my case, a value between 50 and 130 seems to work fine. I'll add some random spawn rotation to our lightning shapes to create more variations in my effect by setting the sprite rotation mode to random. That's already better. We can feel the pop of lightnings now. We might have too much lightning though, so we'll go back to the spawn rate menu and set the spawn probability parameters value below 1. Something like 0.5, which represents 50% chance of spawn probability, works fine to me. It's starting to take shape, but do you know what we are missing right now? Some lights. So, let's spawn some real-time lights each time a lightning particle is spawned. In the render stage, add a light renderer. Untick Use Inverse Squared Falloff option and tick Affect Transparency and Alpha Scales Brightness. That way, we get easily perceivable light that have the same color and transparency value as our lightning particles. We can now increase the radius scale and default exponent values of our light. The radius scale value can be interpreted as the light's intensity, and the default exponent value will act as some kind of attenuation radius. The higher the value, the softer the light will be. Our lightnings are looking good, but they are quite lonely, so let's add some sparks. This final touch to our effect will be quite important and will add a lot of visual noise to our rather plain effect. We'll need the basic alpha blend transparent material we've made at the beginning of the video, a glowing dot texture, and 6 Niagara emitters. Don't worry, it might seem like a lot, but they are in fact quite similar to one another. You'll see. But first, we'll create a material instance from our transport material, the one we've made for the Blood Halo component. Don't forget to rename it. And now, we'll get to the texture part. We need a simple glowing dot. After creating another 512 by 512 document, I'll use a hard brush and apply a single stroke at the center of the canvas. Apply a subtle Gaussian blur filter on it to avoid it being too sharp. Then, I'll duplicate the layer, apply a more pronounced Gaussian blur filter on it, select the screen blending mode, and we're done. After we've imported our texture, we'll be able to assign it to our material instance we previously created. We got everything we need, it's now time to make our sparks. We will still be working inside our first and only Niagara system containing our blood halos and lightning particles. For sparks, we want all our emitters to spawn tiny particles that have lifetime and size variations. They will emit light and collide with the world. Why do we need 6 emitters then? In the first place, we want blue particles emitted from 3 different types of emitters. One constantly emitting particles in a cone shape, one sometimes emitting particles in all directions, and one emitting a burst of particles when lightning particles spawn. And in the second place, we'll duplicate these 3 types of emitters to have not blue but orange particles in smaller numbers. Let's tackle the first type of emitter, the one constantly emitting particles in a cone shape. Let's create a new emitter. The Fontaine template will have most of the modules we need to make our sparks emit through a cone shape. First, we'll go to the emitter state and set the lifecycle mode to system. to have the same loop direction and behavior as the rest of our emitters. In the sprite renderer module, we'll assign our glowing dot material instance, and we'll also set the alignment parameter to velocity aligned. That way, we'll be able to have our particles facing towards the direction they are emitted and squish them to fake a feeling of speed. To squish our particles, in the particle update stage, we'll add the scale sprite size by speed module and keep the min and max scale factor x value to 1 and set the y value to a value above 1. In my case, 1.5 and 4 seem to scale my particles on the y-axis just enough with their speed to not look too off and accentuate the speed feeling of my sparks. In the shape location, we set the shape primitive to a cone and set the cone length to 0, for it will better suit the usage of this emitter that will spawn particles from the end of a swinging cable. In the add velocity module, I'll tweak the velocity speed min and max values and untick the distribution along cone axis and speed follow from cone axis. I'll be able to edit the cone axis to match the direction in which I want my particles to be emitted. In my case, I know that I want my particles to be emitted along the x-axis. This will match the swinging direction of my cable animation. In the spawn rate module, we'll set the spawn rate type to a random range float and set a small range between the minimum and maximum spawning rate value. In the initialize particle module, under the particle spawn stage, we set our sparks lifetime mode to random and set min and max values around 1 or 6 seconds. That should be enough lifetime for sparks to spawn and bounce maybe once or twice with the terrain, depending on the height it will fall. We'll set the color to a bright value above 1 to make our sparks glow a bit, and tweak to our will the uniform sprite size min and max values. In the scale color module, we'll make an easing curve by dragging up the left handle of the last key. This will keep our particles alpha up a bit longer during their lifetime. We want our particles to bounce on our level ground. We can do that by adding in the particle update stage the collision module. In this module, we'll be able to set the bounciness level of our particles in the restitution parameter. I'll set a random range float between 0 and 0.2 to have some particles with no bounce and some being able to bounce at least once. I'll do the same for the friction during a bounce, which represents the lost percentage of velocity after the particle bounced. I'll also tick the advanced aging rate parameter and set its value to 1. And just like with our lightning particles, let's add some light attached to our particles by adding to the render stage the light renderer module. Untick inverse squared falloff and tick FX translucency and alpha scale brightness. It will be up to you to choose the radius scale and default exponent values accordingly to your sparks particle size. And we got our continuously spawning blue sparks emitter. Don't forget to rename it. You can duplicate it and change the spawn rate values and color to have few particles with a complementary color to avoid having a monochromatic effect. It's not looking too great right now. Sometimes you can't rely too much into Niagara's preview window for some types of effect, and this one is one of those kinds, for it will be moving around when we'll attach it at the tip of a swinging cable. So it's better in this case to be able to see it in action in your level. But not for now. We'll first set up all our sparks emitter, then we'll attach our Niagara system to our cable, and then we'll be able to fine-tune our spawning particles numbers, emitting shape angle, and so on. Next emitter will be similar to the one we just made, except instead of emitting in a cone, it would emit sparks in all directions. It would be pretty simple. Just duplicate your continuously spawning blue spark emitter and lower the spawn rate values to have only few particles emitted, with some dead times where no particles are emitted to add that sweet randomness and variation to our effect. In the Add Velocity module, set the velocity mode to from point. And that's it. Just like we did for the previous emitter, you can duplicate this one, set a lower value in the spawn rate module to have fewer particles being emitted, and set a complementary color. Don't forget to rename your emitters. And for our last emitter, the one emitting a burst of sparks when lightning particles spawn, we'll duplicate our continuously spawning blue sparks emitter. We will first configure the spawn of particles from the emitter to be synced with the spawn of lightning particles. To do that, we'll go to our lightning particle emitter and click on the emitter properties stage. In it, we're going to tick the requires persistent IDs parameter. This will allow our emitter to read and track data of our lightning particles, specifically the particle buff time. In the particle spawn stage, we're going to add the generate location event module, which will contain some of the particle data we've talked about a second ago, such as its velocity, acceleration, ID, or buff. We'll set its event probability to a value below 1. This will avoid having 100% chance of spawning burst of sparks at each lightning particle's birth, and thus having too many particles at once and having an effect too noisy. Back to our spawning sparks emitter. We'll delete our spawn rate module. We won't need it. Remember, we want a burst of particle, not a constant spawn rate. We'll also tick the requires persist IDs parameter in the emitter properties stage. We'll then click on the stage icon here, add an event handler, and we set the source parameter to the location event of our lightning particle emitter. This event handler module will now read the location event data concerning our lightning particles. We want the execution mode to be set on spawned particles. Tick the random spawn number, set the max events per frame to 1, and set a random number of particles being spawned at the burst of each of our lightning particles. Note that in this case, the spawn number parameter here is the max value of spawned particles. Now that we got our burst of sparks synced with the burst of our lightning particles, we can make those sparks particles a bit more important than the one being continuously emitted to distinguish them from the others. You can up the color value and the spread sizes, for example. And that should do the trick. Just like we did before, feel free to duplicate this emitter to get a burst of particles with your complementary color and a smaller number of spawned particles. Don't forget, keep your work clean and organized. Take the time to rename your emitters, and if you feel like it, add some comments to group them. Now that the effect is done, I want to attach it to this cable while it's playing its swinging animation in play mode in my level. The cable asset that I have here is a simple rigged subdivided cylinder with a looping swinging animation made in Blender. It will be easy to assign a socket that will hold my spark effect in one of the bones of the cable's armature. That way, my effect will be a child of this socket and always follow the socket's location and rotation. After you've imported your FBX on its animation in Unreal Engine, double-click on your FBX skeleton mesh asset. I can open the skeleton tree window to display the armature of my rigged cable. I want my socket to be located at the end of the cable, if possible, as a child of a bone near the cable's tip. After selecting the desired bone, right-click and select the Add Socket option. You can rename the socket if you want and adjust its position if needed. I have my socket that will hold my spark effect at the end of my cable ready. Now, to make my cable automatically play its animation in my level, I'll create a blueprint class asset and select the actor parent class. I'll go to the viewport window and drag and drop my cable skeleton mesh asset in the components window. After selecting it, in the animation submenu, in the animation mode parameter, I'll select the use animation asset and assign my cable swinging animation. You should be able to see your animated asset playing the assigned animation in the viewport window. Now, I drag and drop my Niagara system in the component window as a child of my cable skeletal mesh asset. After selecting it, in the socket submenu, I can assign the desired parent socket to attach my spark effect onto. And now, we should be able to see both the animation of our mesh and our Niagara system parented to our previously designated socket. We can save our blueprint and drag and drop it into our level. The animation should play when you hit the play button in the editor. You can take some time to tweak some of your VFX values such as particle sizes or spawn rate to better fit the scale of the environment we put our assets in. And that concludes this video. More VFX content is coming on the channel, so stay tuned. Wishing you great Christmas Eve and holidays, folks. Bye!